Welcome to this problem explanation video. Today, we are diving into LeetCode problem number 1544, Make the String Great. This is a fun and insightful string manipulation problem that will help sharpen your skills with stacks and strings. Let's break it down and explore the best approaches to solve it. Stay tuned. The problem asks us to work with a string S that is made up of both lowercase and uppercase English letters. The goal is to transform this string into what we call a great string. A string is considered great if it does not contain any two adjacent characters that are the same letter but have different cases. For example, the pair AA or AA would be considered a conflict because they represent the same letter in different cases. To fix this, we are allowed to repeatedly remove such conflicting pairs. When we do this, the string collapses, and new adjacent pairs may need to be checked and removed. The process continues until no more conflicting pairs remain. Finally, we return the resulting string, and if the string becomes empty, we return an empty string represented by double quotes. It is important to note that the problem guarantees the solution will always be unique for the given input. Now, let's look at the input and output format. The input is a string S that consists of only lowercase and uppercase English letters, and its length is guaranteed to be between 1 and 100. For the output, we need to return the resulting string after all the conflicting pairs have been removed. To understand this better, let's walk through an example. Suppose the input string is S equals LeetCode. In this case, we can identify the first conflicting pair as EE, which occurs at indices 2 and 3. Removing this pair gives us the string LeetCode. After this removal, there are no more conflicting pairs, so the final output is simply LeetCode. This demonstrates how the process works to systematically remove conflicts and simplify the string. Here's another example to further clarify the process. If the input string is S equals ABCC, the first conflicting pair is BB, located at indices 1 and 2. Removing this pair results in the string AACC. Next, we find another conflicting pair, AA, at indices 0 and 1. Removing this pair simplifies the string to CC. Finally, we encounter the last conflicting pair, CC, at indices 0 and 1. Removing this pair leaves us with an empty string. Since there are no characters left, the output is an empty string represented by double quotes. This example highlights how multiple rounds of removals may be required to fully resolve all conflicts. In contrast, let's consider an input where no removal is needed. For example, if S equals S, the string consists of only one character. Since there are no adjacent characters, no conflicts can exist. As a result, the string remains unchanged, and the output is simply S. This example demonstrates that not all inputs require modifications. The constraints of the problem also emphasize that the input string will always have a length between 1 and 100 and consist only of English letters, both uppercase and lowercase. These constraints help ensure that the solution is both practical and efficient within the given limits. Finally, let's explore additional edge cases. One scenario is when every letter in the string cancels out due to conflicts. For instance, if S equals AABBCCDD, each adjacent pair conflicts, and removing them all results in an empty string. Here, the output would be. Another scenario is when the input string contains no conflicts at all. For example, if S equals ABCXYZ, all the adjacent letters are either different letters or have the same case, so no removals are necessary. The output, in this case, is simply ABCXYZ. Lastly, a single letter input like S equals Z also has no conflicts since there are no adjacent characters to compare. The output remains Z. These examples cover a variety of situations that could arise based on the structure of the input string. To solve this problem, we first considered two main approaches. The first is the brute force approach, which works by iteratively checking for adjacent characters in the string that are the same letter but in opposite cases, such as at ANDA. When such a pair is found, it is removed, and the process starts over from the beginning of the string. This ensures that all invalid pairs are eventually eliminated. However, the key observation here is that removing one pair can affect the validity of neighboring pairs, which is why the algorithm needs to start over repeatedly. While this approach is simple to implement, it is highly inefficient because the string must be rescanned after each removal, leading to a time complexity of O(n) squared, in the worst case. On the positive side, it uses O(1) space since no additional data structures are needed. Next, we considered an optimized approach that uses a stack, which provides a more efficient way to solve the problem. The idea is to traverse the string while using the stack to maintain only the great portion of the string. For each character, we check whether the top of the stack forms a conflicting pair with the current character. If it does, we pop the stack to remove the pair, otherwise, we push the current character onto the stack. This eliminates the need for repeated rescanning. By using the stack, we can efficiently handle the cascading effect of removing pairs. Once the traversal is complete, the stack will contain the great version of the string, which can then be converted to the final result. One important detail here is how we identify conflicting pairs of characters. This can be done using the condition abs, ord C1, ord C2, = 32, which checks if the two characters differ only in their case. The stack inherently manages the cascading effect, ensuring that we only need one traversal of the string. This results in a much more efficient solution with a time complexity of O(n), since each character is pushed onto the stack at most once and popped at most once. However, the space complexity is O(n) in the worst case, where no pairs are removed and the stack holds all the characters. We also briefly explored alternative approaches, such as a two-pointer method or a recursive solution. While these could work, they introduce additional complexity in managing the cascading effect of pair removal. The two-pointer approach modifies the string in place, but it is less intuitive. Recursive solutions, on the other hand, mimic the brute force behavior and are prone to inefficiency and stack overflow for larger inputs. Ultimately, we chose the optimized stack-based approach as the best strategy for this problem. It strikes a balance between efficiency and simplicity. By processing each character only once and relying on the stack to handle cascading removals, we avoid the repeated rescans required by the brute force method. This makes the stack solution highly time efficient, with an O(n) time complexity that is suitable for larger strings. While the brute force approach has the advantage of O(1) space complexity, it is far too slow for larger inputs, such as strings with lengths up to 10 to the power of 5. On the other hand, the stack approach does require O(n) space, but this trade-off is justified by the significant improvement in time performance. Alternative methods, such as the two-pointer or recursive approaches, further reduce space usage but come with added complexity and are less intuitive to implement. The key takeaway here is that the stack-based solution is optimal for this problem. It is efficient, easy to understand, and practical for real-world use cases, making it the clear choice for processing the string in linear time. To solve this problem, we need to simplify the given string by repeatedly removing adjacent pairs of characters that are the same letter but in opposite cases, such as at and a. This process continues until no such pairs remain, and the result is the simplified string. To achieve this efficiently, we can use a stack data structure. The stack allows us to track the characters we've processed so far and quickly remove pairs when needed. First, we initialize an empty stack. Then, we iterate through the string character by character. For each character, we check if the stack is non-empty and if the top of the stack forms an oppositely cased pair with the current character. This approach ensures that we handle the problem incrementally and efficiently, leveraging the stack's last-in, first-out property to manage pairs dynamically. Now, let's break down the process of checking for opposite case pairs. To determine if the current character and the top of the stack form such a pair, we calculate the ASCII difference between them. Specifically, the condition abs, ord, current_char, ord, top_of_stack, == 32 confirms that they are the same letter in opposite cases. If this condition is met, we pop the top character from the stack to remove the pair. Otherwise, we push the current character onto the stack. This ensures that only unmatched characters remain in the stack. By repeating this process for all characters in the string, we gradually eliminate all oppositely cased pairs. When the iteration is complete, the stack contains the simplified string but in reverse order, as characters were added and removed from the top. Finally, we reverse the stack and join its contents to construct the final result, which is the simplified string. The choice of a stack is particularly important for this problem because it allows us to efficiently backtrack and remove previously added characters when we encounter an opposite case pair. Without a stack, we would need to restart the traversal repeatedly or use additional logic, which could lead to significantly worse performance. By using a stack, each character is pushed and popped at most once, resulting in an overall time complexity of O, n, where n is the length of the string. Additionally, the space complexity is O, n, in the worst case, which occurs when no pairs are removed, and the entire string remains in the stack. We should also account for some edge cases. If the input string is empty, we simply return an empty string. If the string has no removable pairs, the original string is returned unchanged. On the other hand, if all characters are removable, the result will be an empty string after processing. The problem revolves around two key data structures. First, the stack is the main tool we use to process the string. It stores the characters as we iterate through the string, enabling us to efficiently remove adjacent pairs with opposite cases whenever they are detected. Second, the string itself is important as both the input and the format in which we return the result. After processing the input string using the stack, we reconstruct the final result by converting the stack back into a string. This combination of the stack for processing and the string for the final output ensures that the solution is both efficient and straightforward to implement. To better understand how this algorithm works, let's walk through a visual example with the input string A of BCC. We start with an empty stack. First, we process it and push it onto the stack, resulting in a. Next, we process a. The top of the stack is a, which forms an opposite case pair with a, so we pop a from the stack, leaving it empty again. We then process B and push it onto the stack, giving B. When we process B, it forms an opposite case pair with the top of the stack, B, so we pop B, leaving the stack empty once more. We repeat this for C and C, pushing C and then removing the pair when C is processed. At the end of the iteration, the stack is empty, so reversing and joining its contents gives us an empty string as the final result. The algorithm achieves a time complexity of O, n, because each character in the string is pushed onto the stack and removed from it at most once. This ensures that the processing time scales linearly with the length of the string. In terms of space complexity, the stack requires O, n, space in the worst case, which happens when no pairs are removed, and all characters remain in the stack. These complexities make the solution both time-efficient and space-efficient for handling strings of varying lengths, ensuring that it performs well even for edge cases and large inputs. The function makeGood simplifies the given string by removing adjacent pairs of characters that are the same letter but have opposite cases. Step-by-step explanation. 1. Stack initialization. A stack is used to keep track of the characters in the simplified string. It starts off as an empty list. 2. Iterating over each character. A loop is used to iterate through each character in the string S. For each character, we check whether the stack is non-empty and the top of the stack forms a conflicting pair with the current character. This is determined using the ASCII values of the characters. The absolute difference between their ASCII values must equal 32, e.g., A is 97 and A is 65, so 97 minus 65 is equal to 32. 3. Removing conflicting pairs. If the conditions for a conflicting pair are met, the top character in the stack is removed using stack.pop. Otherwise, the current character is added to the stack using stack.append, char. 4. Returning the result. After processing all characters, the stack contains the simplified string. The characters in the stack are joined together using .join, stack, to form the final solution. Edge case handling. If the string is empty, the loop does not execute, and the function directly returns an empty string. If no conflicting pairs exist, the entire string is returned as is. This solution is efficient with a time complexity of O, n, where n is the length of the string, as each character is processed at most once. The space complexity is also O, n, in the worst case, where all characters are added to the stack without any removal. This ensures it handles edge cases and large inputs effectively. This is the Java implementation of the LeetCode problem number 1544, make the string great. The solution uses a stack to process the input string, mirroring the logic of the provided Python solution. The stack is used to store characters as we iterate through the string, and characters are removed if they form a bad pair, i.e., when their ASCII difference is 32. This Java implementation uses Java's stack class for the stack operations and a string builder to construct the final result efficiently. Key differences include explicit type declarations and the use of Java-specific collections. To solve this problem, we use a stack-based approach. First, we initialize an empty stack to keep track of characters as we process the input string s. Starting with the first character, we check the stack, which is currently empty, and add it to it. Next, we process the second character, b. Since the stack contains a, we simply add b to the stack, resulting in a b. Now, for the third character, b, we check if it is the opposite case of the last character in the stack, which is b. Using the condition abs, ord b equals 32, we confirm that it is. As a result, we remove b from the stack, leaving us with a. Now we move to the fourth character, a. The last character in the stack is a, and again we check if they are opposites. The condition abs, ord equals 32 evaluates to true, so we remove a from the stack, leaving it empty. For the fifth character, c, since the stack is empty, we add c to it. Finally, we process the sixth character, c. The last character in the stack is c, and we verify that c and c are opposites using the same condition, which evaluates to true. Therefore, we remove c from the stack, leaving it empty once again. At the end of processing all characters, the stack is empty, which means the output is an empty string. In the next example, we process the input string s equals LeetCode. First, we initialize the stack as empty. Starting with the first character, L, we add it to the stack, resulting in L. The second character, E, is added to the stack as well, making it LE. For the third character, E, we check if it is the opposite of the last character in the stack, E. Using the condition abs, ord E equals 32, we confirm that they are opposites, so we remove E from the stack, leaving L. Next, the fourth character, E, is added to the stack, resulting in LE again. Continuing with the fifth character, T, we add it to the stack, updating it to LET. For the sixth character, C, it is simply added to the stack, resulting in LETC. The seventh character, O, is also added, making the stack LETCO. Similarly, the eighth character, D, is added to the stack, updating it to LETCOD. Finally, the ninth character, E, is added to the stack, leaving us with LETCODE. After processing all characters, the stack contains all these letters, so the output is the string formed by combining them, which is LeetCode. In this example, the input is s equals a_b_c_c. As usual, we start with an empty stack. The first character, a, is added to the stack, resulting in a. For the second character, a, we check if it is the opposite of a using the condition abs, ord equals 32. Since this is true, we remove a from the stack, leaving it empty. Next, the third character, b, is added to the stack, updating it to b. The fourth character, b, is then checked against b, and since they are opposites, we remove b from the stack, making it empty again. For the fifth character, c, we add it to the stack, resulting in c. Finally, for the sixth character, c, we verify that it is the opposite of c using the same condition, which evaluates to true. We remove c from the stack, leaving it empty once more. After processing all the characters, the stack is empty, and the output is an empty string. This demonstrates how the algorithm systematically removes pairs of opposite case letters, leaving only the characters that cannot be paired. The time complexity of this solution is O(n), where n represents the length of the input string. This efficiency is achieved because the algorithm processes each character of the string exactly once. As it iterates through the string, it performs two types of stack operations, pushing and popping characters. Both of these operations are constant time, O(1). Since every character in the string is pushed onto the stack at most once and popped at most once, the total number of stack operations is directly proportional to n. Therefore, the dominant operation in this algorithm is the single traversal of the string, solidifying the overall time complexity as O(n). In the best case, where no adjacent characters need to be removed, such as in a string like ABCDF, each character is pushed onto the stack, and the algorithm processes the string in linear time. Even in the worst-case scenario, where characters are removed in alternating pairs, such as AAAAAA, each character still results in a constant number of operations, including a push and a pop. In the worst case, the stack could hold all n characters, as in an input like ABCDEF. When examining the best, worst, and average case scenarios, we find that the time complexity consistently remains O(n). Additionally, the space complexity of O(n) arises from the stack, which stores characters that are not immediately removable. The final output string, created using the join operation, also requires O(n) space, but this does not change the overall space complexity, as the stack is the dominant factor. Similarly, in the average case, the input string undergoes partial reductions, but the total operations remain proportional to n. The total space complexity of the algorithm is O(n). This is primarily driven by the stack, which can grow to accommodate all n characters in the worst case. Temporary variables, such as the one used to store the current character during iteration, only require constant space, O(1). Meanwhile, the space used for the final output string is also O(n), as it involves joining the characters stored in the stack. When comparing this approach to a brute force or naive method, the differences become clear. A naive approach, which repeatedly scans the string to remove adjacent bad pairs, would require multiple passes over the string. This could result in a time complexity of O(n²) in the worst case, such as when reducing a string like AAA. In contrast, the stack-based approach avoids redundant operations by processing each character exactly once. This results in a significant improvement, reducing time complexity to O(n), while maintaining an efficient O(n) space complexity. To mathematically confirm the big O efficiency, consider the time complexity. Let n be the number of characters in the input string. Each character is pushed onto the stack at most once and popped from the stack at most once. This means the total number of stack operations is bounded by 2n. While this might seem significant, it simplifies to O(n), as constant factors are discarded in big O notation. For space complexity, the stack can grow to hold up to n characters in the worst case, requiring O(n) memory. No additional data structures contribute more than this, ensuring the total space complexity remains O(n). In conclusion, the stack-based approach is both time and space efficient, achieving O(n) for both complexities. This makes it far superior to the naive O(n² approach, especially when handling larger input sizes. When tackling this problem, there are several common mistakes to watch out for. First, not handling edge cases like empty strings or single character strings can lead to runtime errors, such as index out-of-bound issues, or incorrect assumptions about the input size. Always ensure your solution works for inputs like an empty string or a single character, such as a. Another mistake is ignoring the problem constraints. For example, if the maximum string length is 10 to the power of 5, using a nested loop approach with O(n²), complexity will almost certainly result in a timeout. It's important to design solutions that respect these constraints. Additionally, correctly identifying the match condition is crucial. For this problem, you need to check both the character values and their case relationships, such as ensuring the absolute difference between their ASCII values is 32. Forgetting this can lead to incorrect results. Overcomplicating the solution is also a frequent pitfall. Many candidates unnecessarily use advanced data structures like hash maps or stacks, even when a simpler approach suffices. Lastly, consider in-place operations whenever possible. Modifying the string directly can save memory and speed up execution, so missing this optimization might result in less efficient code. Now, let's explore some insights that can help during interviews. Recognizing patterns is key. Problems that deal with adjacent character pairs, like this one, often benefit from stack-based or two-pointer techniques. Identifying patterns such as opposite case relationships or adjacent duplicates will guide you toward the right approach more quickly. Additionally, be mindful of trade-offs. For instance, a stack-based solution with O(n) space may be simpler to implement, whereas a two-pointer approach can achieve O(1) space but might require more careful handling. Once you've implemented your solution, always check its optimality. If the time complexity is O(n²), think about whether a linear pass is achievable and why your current approach might fall short. Interviewers also value a thorough understanding of edge cases. proactively discussing inputs like empty strings, sequences of identical characters, or strings with only opposite case pairs shows that you've thought deeply about the problem. Lastly, it's helpful to be aware of related problems, such as LeetCode 1047, 1209, 946, and 844, as they share similar concepts and can provide additional practice. Finally, let's compare some alternative approaches and their trade-offs. A brute force solution, which operates in n² time, involves scanning the string repeatedly and removing adjacent pairs as they are found. While straightforward to implement, it becomes inefficient for large inputs. A more common approach is stack-based, running in n time. Here, you push characters onto the stack unless they form an opposite case pair with the top element, in which case you pop the stack. This method is efficient and intuitive but requires extra space. The two-pointer technique also achieves n time but optimizes for space by modifying the string in place. It uses a right pointer to maintain the valid portion of the string, which minimizes memory usage but demands careful index management. Lastly, the recursive approach involves removing adjacent pairs and calling the function again until no pairs remain. While elegant in theory, it can lead to stack overflow for deep recursion levels, especially with large strings. Each of these methods comes with its own advantages and drawbacks, so understanding when to use each one is essential for writing efficient and robust solutions. Great work! We've covered the key insights for solving Make the String Great. Remember the importance of choosing an efficient data structure like a stack for problems like this. If you found this video helpful, don't forget to like, share, and subscribe for more content. Keep up the great work, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!